All right. So if we're going to study a chapter on gases, we need to know that's a different kind of an animal. We don't know what the volume of a gas is. As a matter of fact, what's the density of a gas? You got to be careful about that too. If I look up in a book, what's the density of steel? It's going to give me one number. Well, how do they know how much steel I have? It doesn't matter. It's a ratio, isn't it? A ton of steel has the same density as a BB of steel. You get that? And so, okay, what if I look up the density of a liquid? They give me one number, just one, because they can't be compressed either, and it's pretty much going to be a single number. But if you look at what's the density of air, you're going to see page after page after page of density numbers, because air at one temperature, if it's warmer, it's less dense, less dense, less dense. If it's colder, it's more dense. And so the density of a gas can change greatly. And that's why you aren't going to see one number there. Now, I will show you a number here in just a minute, the density of air, but it'll say at this temperature. And so we will look at that. Okay, hot air balloons. We will talk about hot air balloons in this chapter. And if you think about it, I've had people go to a swimming pool, and let's say they have a little trouble staying, having their head above water. You throw in one of these little noodles. Remember those swim noodles? And no problem. That little tiny noodle is enough to keep them up, isn't it? And so, okay, why don't I say, hey, why don't you go up in the air? Why don't you let the buoyant force of the air lift you up? Because the buoyant force of the water is kind of pushing you up, isn't it? And you say, I can't, I'm falling, you know? Well, how big of a little pool toy do I need to give you to get you to go up in this ocean, in the ocean of air? And it's got to be big. Why does a hot air balloon have to be so big? What do you think? That little pool noodle, right? It's displacing what material? Water. Okay, water is about 1,000 times more dense than air. So I only have to displace a certain amount of water to give me that extra buoyant force to kind of keep me up. What about here? What if I want to keep up in this ocean of air? I need a big pool noodle, don't I? Because you got to displace a lot of air to equal your weight, or even to help you lift you up. So we'll talk about hot air balloons later too. I do want to make sure that some of the basics are done. I don't care what book you look at. You're either going to see 78, 79. It's going to be something close to 80%. The air that you live in is about 80% nitrogen and about 20% oxygen. And again, some books will cut that down and tell you 1% this or 0.5% that. And we'll take a look at that. But that's kind of what you're looking at. So, but then we have this other thing that makes it so different. And so the handout sheet I gave you has a great picture in it. And I'm going to show you that picture. Here it is. This is so different than solids and liquids because take a look at that picture right there. If I took you to the bottom of the ocean of water and I said, get out, you'd be killed. That's another thing we think about. Why would you be killed because you're a mile down in the water? So what? You're a mile down in the water. Just get out. Why would you be crushed?
Pressure.
And that's something I want to talk about also this chapter. Pressure cannot kill you. Difference in pressure can kill you. What is the pressure on one side of that piece of glass? It's huge. The pressure on that glass is huge. I'll show you how to calculate that. It's huge. Why isn't the glass breaking?
Pressure on the other side.
Yeah, the other side has the same pressure. Pressure doesn't kill you. A difference in pressure can kill you. When a tornado goes by, what do you think? A lot of people think it's the wind. The wind pushes the glass. No, that's not what happens. The tornado is a very big low pressure area. So I have air in here at a normal pressure, and outside the tornado is really low, really low. That makes a big difference in pressure. And what happens to the window? It doesn't come in. It gets blown out. And so we're going to talk about that as far as pressure differences. Yes?
Is that why in like when like movies and stuff, when like an airplane window breaks and it gets pushed out?
If you now we'll talk about that too, but if I am in an airplane way up high, there's almost no air pressure outside the plane, but they pressurize the plane so you don't die. Okay, so they take extra air with them and pressurize the plane when they go up there so you won't die. And the ship is made strong so it doesn't just open up. That'd be bad. But if somebody in movies, when they shoot a hole in a plane, that's usually not good. And so what happens is the pressure inside the plane is trying to equalize out there, and if you get in the way, it pushes you out the window. And they always love movies where the overweight person, the little person gets thrown up through the window and they're gone. And then the overweight person, they form like a cork. And they love movies. They love to do that kind of thing there.
Like the end of Goldfinger.
And what now?
The end of Goldfinger.
Goldfinger. Let me think about that.
James Bond movie.
Wow, that was a long time ago. I think I saw that like 30 years ago. I have not seen it lately. What happens in Gold?
At the end, he tries to shoot Bond and misses and hits the window.
Oh,
And
okay.
shatters
Does
and
he?
he's sucked out.
Okay. And I will try to prove to you, beyond a shadow of a doubt,
Pushed out.
that nothing sucks in science. Nothing sucks. There's a lot of pushing. There's a lot of pushing going on. No sucking. Anyway, take a look at this. This picture here is so telling because if I had a block of wood, it would have about the same density throughout the whole block of wood. If I had a column of water, it would pretty much have about the same density everywhere you go. But look about air. What about a column of air? And I know what I was telling you. At the bottom of the ocean, the reason you're being killed, you can be killed. Your body, first of all, there's a huge amount of pressure. Where's the pressure come from? It comes from the weight of the water above you. If you have a mile of water above you, that's a lot of weight. And because it's a fluid, you'll not only feel that pressure this way, you'll feel it in every direction. So the mile of water is going to weigh a huge amount. But guess what? You live at the bottom of an ocean. You live at the bottom of an ocean of air. You should be crushed. So the good news, God made our bodies. We have fluids in our body. We have air in our body. We have fluids. And we actually can push back the same amount that the air is pushing on me. And that's why I don't die. I should die. There's enough pressure on me right now to kill me. But my body's able to push back with the same amount. So that's why I don't get hurt. Sometimes they'll find fish. They'll go down like half a mile in the water and they'll capture a fish and say, wow, there's a new species. I've never seen that before. And then they used to just bring them up. And then bring them up, and everything that was made out of air or anything like that, it would expand. And by the time they got to the top, the fish was a mess. It was blown up. And then they had to learn how to put the fish in a pressurized container and then bring it up and then keep it under pressure if they want to look at it. Does that make sense? So if you take a fish a half a mile down and bring it up and it expands and blows up, then what's happening to you if I take you up in this ocean? What if you go up to the mountains? What if you go up higher? What's going to happen to you? What do you think happened to pilots when at first we were flying here? Nice little planes. Then they had these jet planes, and they said, how high can we go? And what was happening when they went higher and higher and higher? What happens to the atmosphere when you go higher and higher and higher? It's less and less and less pressure. And so anything in my body that had air in it, it's going to expand. Another thing that happens is, I'll answer your question in just a minute. If you took plain old water, and had ice cubes in it, it would sit there, right? But if you put it in a vacuum means I'm going to take the air out from underneath there. We say that water boils at 100 degrees Celsius. That's not true. It doesn't boil at 100 degrees Celsius unless it has one atmosphere of air sitting on top of it. So at sea level, water boils at 100 degrees Celsius because one atmosphere of air is sitting on top of that water. But you know what would happen if you took that air off the top of that water? Nothing would keep that water from boiling. It would boil, and the ice cubes would still be in there. Because you think of boiling as you better be pretty hot to be boiling. That's because you had a huge amount of air sitting on top of you. If you take that air off, it'll boil on its own. And guess what happened to the pilots when they went up I was in 4th grade and I saw this picture, and yes, the books were in black and white. But anyway, I remember this pilot, and he had a G suit on. I didn't know what that meant. And what happened is a suit that was actually producing pressure, because with no pressure here, everything in his body wanted to come out. And so he had a pressurized suit on. And they had a beaker of blood in this picture, and they took a picture of him. He was way up high, and the blood was boiling. It was cold, but there was almost no atmospheric pressure, and blood was just starting to boil. It wasn't hot. It was changing from a liquid to a gas at a cold temperature. So this is such an interesting chapter. It's just so many things I can show you, and you'll see it all over your whole life. You'll be able to see things like this. What I was telling you is you live at the bottom of an ocean of air, and this is the most dense air. If I go to sea level, that's the most dense air it can be in. If I go up, it's less dense, isn't it? I remember almost always when if we're going to go take a trip and let's say we're going up a mile up to the mountain somewhere, and maybe it happens to be a mile above sea level, right? You got your potato chip bags, because we like to take food with us, so you don't have to buy it. And when we get there, he said, look at the potato chip bag. It's like somebody blew it up. It's like really plump. It wasn't plump when I bought it. So what happened there? The air inside, as you took away some of the air pressure here, and that's what makes it really plump. How many people have ever seen that before? Did you ever wonder why, or you knew why?
Well, me and Colleen know why, because Caroline, she goes to college up in the mountains. So anytime we bring her food or she brings food back, it's always either deflated or inflated.
Interesting. So if they buy something at the store up there and you bring it down, I've never seen that. It actually deflated, right? Because the pressure here is greater, so it looks like it's more compact. Ooh, interesting. That's interesting. All right. I do want to show you some numbers here. This picture right here, can everybody see that picture right there? Well, first of all, where is the atmosphere? Where is the Earth's atmosphere? And Walker, I apologize. Let's go back. You had a question.
Oh, I forgot.
Wow. I'm sorry.
No, that's
Can you, if you remember, just raise your hand again, okay?
Okay.
All right, so let's take a look here. And these are in kilometers, but I went ahead and converted it to you some miles so it kind of makes sense to you. Almost all of the weather, almost everything that has to do with weather, clouds and stuff like that, that's going to happen in probably less than a 6-mile thing. I mean, if you're up 5 miles, you are way, way up in there. Get that? And so you're even above the clouds and everything. So most of your weather is taking place down here. And then, is there still air above that? Yes, there is. But notice that the author says about 90% of the atmosphere is below the 12-mile range, 20 kilometers. And this number is going to show up all the time. This number is going to show up in this chapter all the time. 99% of the air is going to be found at 30 kilometers or lower, and that's about 18 miles, okay? So when you see that word 30 kilometers, you just tell yourself, that's kind of the top of the atmosphere. Now, even if I went beyond that, would there be little bits of nitrogen and oxygen? Maybe here's one. I can't. There's no like definite line, is there? And so, but we know that when you keep seeing this 30 kilometers, that means atmosphere. So right now I have about 30 kilometers of air sitting on top of me. It's sitting on top of me, and it's pushing in every direction. And again, luckily, my body can push back with the same amount of pressure so I don't get killed. Now, I don't want to get too personal here, but if I were to take your body and tape up every opening in your body, except for one, and then I hooked up a vacuum pump to it, if I could pump out all of the air inside your body and you're still having fluids, you would be crushed. You would be crushed because of the air outside you. I will also eventually, not today, I will show you a demonstration where nothing sucks, and I will prove to you that even when you use a straw, you are not sucking that liquid up the straw. And I'll even show you a situation where you think, go ahead, suck the liquid up a straw. You won't be able to. And you'll eventually figure out that what you're really doing is taking the air from the inside of the straw and putting it in the back of your throat. So you did take the air in the straw and move it back here. And all this air says, I'm going to equalize that vacuum. Trying to get in, try to get in, try to get in. If you, believe it or not, you're not going to believe this, but the easiest way to equalize the pressure is for the atmosphere to push on the soda and push it up into the vacuum. And when you use a straw, the air pressure is actually pushing the liquid right up into your throat. And I know you don't believe that, but I'll set up a demonstration on Monday, and I'll try to prove it to you that's not you're not sucking anything. If you've ever had a really thick milkshake and you want to have a straw, if it's really a thick milkshake and you, quote, suck on it, why does the straw collapse? Well, because I'm sucking really hard. Was your sucking touching the straw? How is your sucking making the sides of the straw go in? But what actually happened is you take the air of that straw, this air is going to try to get in. Can't get in, can't get in, can't get in, can't get in. I'll get in this way. I'll close in that vacuum by collapsing that straw. Really? I got to think differently here. I'll have a vacuum next week. I'll get a vacuum out. I'll prove to you a vacuum cleaner does not suck. It has a motor in it, and it has a fan, okay? The fan takes air that's right here, and the fan, air is right here, and the fan says, see this air? Go over there. Go over there. Okay. And the fan makes the air go over there. Well, what does that leave behind? A vacuum. And the atmosphere says, I'm filling in that vacuum. And so when you use that vacuum like this, you had air being removed from underneath. And this air says, I'm going to fill in a vacuum. And I'm going to get there one way or another, and I'll go through those carpet fibers. Yeah, I will. And anything kind of light, I'm taking it with me. And it doesn't suck up the dirt. The dirt gets pushed into the vacuum. So we have to think a little bit differently, don't we? All right. Let's go to this right here. And if you happen to have a calculator with you, something doesn't look right about this chart. It says here that the density of dry air at 0 degrees, 10 degrees, 20, and 30, they have these numbers, okay? Can everybody see the numbers? Something's not right here. This says that room temperature air has a density of about 1.21. And I think to myself, well, how is that? 1.21, that's like water has a density of 1, I thought. You're telling me air has a density of 1.21? That means air would sink in water. So what's wrong? What's wrong with my thinking here? What's wrong? Yeah.
Well, it's measured in kilograms per cubic meter.
What?
Kilograms per cubic meter.
Oh, okay. So does that make a difference? So one of the questions I will ask you to do, because you guys are all very skilled in physics now, I will ask you to show me using factor label how to convert this into grams per cubic centimeter. Let's try it. All right, what I want you to do is somewhere in your paper, you have 1.21 kilograms per cubic meter, and I want you to convert it into grams per cubic centimeter. That's the most frequently used density unit, and that's the one you're kind of familiar with. So use factor label, see if you know how to convert this from 1.21 kilograms per cubic meter to some number of grams per, and then we can use our idea of water being a density of 1, things like that. All right, let's see if you remember how to do that. Take about a minute. I bet you can do it in about a minute. Does everybody remember how to do this? If you haven't started already, I'll get you started, okay? 1 kilogram is the same as 1,000 grams. All right? Now I'm in grams per cubic meter. Did everybody get that far so far? Okay, now, the distance unit cubed. What? Oh, I remember that. I was certified. Oh, yeah, I'm certified. And we want to change cubic meters into what? Cubic centimeters. All right, that'll do it. That will do it. All right, put that in the calculator. What is the density of air in grams per cubic centimeter? You already have it? All right, what do you got?
0.00121.
Wait, how many zeros?
0.00.
Okay, and 121?
Yeah.
Okay, that's exactly right. So if you thought that chart was trying to tell you that air at room temperature had a density greater than water, you said, wait a minute. Oh, you got me. And Eli, you picked up on that really fast. That was good. Now, what you want to do is, I want you to think about this. I want you to tell me how many times more dense is water than air at room temperature. Now, how do we do that? How many times more dense is water than air? Okay, so you take the big number, divide by the little number. You already have it? Wow, you guys are fast. What do you got?
826.45.
Okay, that's good. Okay.
I got 892.
Uh-oh.
Wrong.
I'll do it again. One divided by 0.00121.
121.
Well, there's your problem, though. You left off a one.
It's still 892.0.
892? Okay, so when I tell you that air is about 1,000 times, it's really about 900, really. It's really closer to 900. But you're talking about something that's, water is about 900 times more dense than air. Okay? And that's how you can play with numbers and kind of understand some things like that. Now, I want to show you something else now. What is the density? Helium. Hey, I've had a helium balloon. And a helium balloon seems to do weird things in the air, doesn't it? A helium balloon does something weird. It kind of goes up, doesn't it? Think about that. Why would a helium balloon go up? What do you think? Is it less dense than air? Okay, let's try it. So by now you probably figured out if you take it and divide this by 1,000, you probably get the number, don't you? So what is the density of helium? 1,2,3,178. Okay, so the density of helium is 0.000178 grams per cubic centimeter. And you say, wow, that's even less dense than air, isn't it? Let's do this now. How many times less dense, or how many times more dense is air than helium? What numbers are you going to put in the calculator now? Raise your hand. You said, I really do know what two numbers to use for this. Okay. All right, that means a lot of you don't, right? All right, what's the density of air at room temperature? You told me it was, where's that number? You said 0.00129, right? 0.00129? Or 0.121? Okay, so 0.00121 is the density of air. And what is the density of helium? 0.000178. All right, do that. Put that in your calculator. How many times more dense is air at room temperature than helium? And since you already answered one, I'm going to see if somebody else has one. Anybody else who has not answered one? Yes? 6.7. Is that what you guys are getting?
Yeah.
Okay, so about 6.7. Okay, so almost 7. So air is also about 7 times more dense than helium. So what's happening to helium? If I make a balloon full of helium, it's going to, does it have a buoyant force on it? Yeah, because it's displacing air, isn't it? Isn't that right? So it has a buoyant force on it, and does it weigh something though? I know you don't think a helium balloon has any weight. It has to. It's made of matter, isn't it? So it has weight, and it has a buoyant force on there. Which one's greater? When I let go of that balloon, and some of you cried, don't tell me out loud, but some of you probably cried when you were younger, and they said, don't let go of this balloon, and you did. Huh? Remember that?
Whose hair
I sh-
steal, so you.
It's been like 10 years, and I remember that day. Remember that? How many of you, honestly, that has happened to you? You remember it. You remember losing a balloon. I know you did. You just don't want to raise your hand. Okay. All right. It was kind of, hey, my grandkids, it's even happened to them, you know. I think it's happened to almost everybody. And it's sad. It's sad to see that balloon go, and it's not coming back, is it? Right. Anyway, so it has a buoyant force on it, and it has weight. But the buoyant force is clearly greater than the weight, and that's why it actually goes up. Another way of saying that is, because it's less dense, it will actually tend to rise. Yes?
There was this episode of the show where they were like talking about how there was a balloon like up in like the top of a, what do you call it, like a warehouse for like 10 years or something, and then eventually it came down like very slowly.
Huh. Okay, now,
That's the helium.
a cheap helium balloon, one that looks like a regular balloon, has helium in it, those are fun for a day. But believe it or not, you don't think so, but that rubber balloon has 1,000,000 trillion holes in it. And oxygen, air, it has trouble getting out of it. The helium's really small. And as that helium is bouncing around, escape, hundreds, thousands, 100,000. And what happens over time is a cheap balloon with helium in it, it's about a day later, you're going to see it on the ground because weight is going to be, it's going to go like this. See that? But if you get the shiny balloons with the mylar, those are mylar. Mylar is a much tighter material, and helium has trouble escaping there. If it does, it doesn't escape very quickly. I've had a helium balloon for a month. I've had a whole month. It's been up, on top of my ceiling. So I think what happened there is, over a long period of time, maybe enough helium would escape, and it would slowly come down. Because if helium escapes, guess what? You have less buoyant force, and then eventually I could see it coming down. I could even see a time where it might sit right in the middle, and then eventually it would come down like that. Those are good questions. Yes?
Does the difference between the density of air and helium have any effect on why you when you inhale helium, it changes the helium?
Yes. Even though I've read 2 or 3 different explanations on that, the one I guess I like the best is that when you vibrate air, if you make a vibration through air of this density, it'll make a certain sound like but if you let it vibrate through materials not as dense, it'll make a higher pitched sound. And so your vocal cords are vibrating, and so what I've heard is when they vibrate and it goes through helium, it makes a higher pitched sound. They have they actually have people who work underwater, and they sometimes have to work underwater for hours and hours. And the problem is, if you know anything about scuba diving, regular air has nitrogen and oxygen in it, because that's what air is. But when you go down really deep, you get all this stuff in your blood, and then you come up, and if you come up too fast, little bubbles of nitrogen will collect in all of your joints, and it's really, really, really painful. And it's called the bends. And so that's why if you're a scuba diver, you have to plan your dive. I'm going down here at 100 feet down. I'll be down here for 20 minutes. Then I have to come up to about 80 feet and sit there. I just sit there and give the nitrogen time to come out. Then I do another one, decompress. So if you're a scuba diver, you have to plan your dives. But if you want to work there hour after hour, all they have to do is give you a tank of not nitrogen and oxygen, but helium and oxygen. Because really, the only thing I need to breathe is the oxygen. So give me 80% helium, 20% oxygen, and I will talk funny. You'll hear me talk funny, but I'll be able to come up. Helium easily comes out of the blood. And so I'll be able to work for hours and hours and hours and just come up, and I don't have to worry about the bends there. Yes?
That's what they do with, I think I don't know the specific name, but it's like super deep divers, but they'll live in a pressurized chamber at the bottom of the ocean, typically working on like oil lines.
Right.
And they have
And so they, if they want to say, I don't want to waste time. Time is money. I don't want to waste time putting you in a decompression chamber or things like that. So now I will say, if you're underneath there already and you have compressed air down there, and you go out and work and you just go back in your building, you're okay. But if you're going out of your building, going up and down, then they're probably going to use a helium oxygen mixture like that. And when you hear them on their intercom system, they always talk funny like that, like the Chipmunks. Remember Alvin and the Chipmunks? Remember, you guys know who that is? Okay, just make sure. Okay, so now I want to show you one more thing here. You're going to see in this chapter, you're going to see some pictures. And the numbers in this chapter, you're going to have to study them a little bit. And I'm going to say the numbers many, many times, so it might help you a little bit here. What's 30 kilometers? How much air is sitting on top of me right now? Essentially, 99% of the atmosphere is how high up? About 30 kilometers. Okay. So when you see this picture here, the person's saying, and I really love the author of this book, Conceptual Physics, because he wants you to have numbers that are not like 0.00056. They don't want their numbers, okay? So he has a straw, and the straw has a cross-sectional area of 1 square centimeter. I can remember that. 1. So it's going to look like that. See that? 1 square centimeter. And that straw goes up how high? Why do they say 30 kilometers? That's the top of the sky. Okay, so that's what he wants. He wants you to think about that. And here's what it says. The mass of air that would occupy a bamboo pole that extends to the top of the atmosphere is how much? And I love that because I can remember 1 kilogram. So if I had a straw like that and it went up about 18 miles up, what would the total mass of that air be? How much? Everybody look at me. How much? 1 kilogram. What would the weight of that air be? 10 newtons. All right. Yes, no? Okay, now watch now. I will show this. I'll show you the calculations here a little bit later. Take a look at this. What if I had an area that was 1 meter by 1 meter? I had a square this big. Let's say on top of the table, 1 meter by 1 meter. What would be the mass of air sitting on top of that table? So how in the world am I supposed to know that? I'll tell you a clue. 1 square centimeter, it would be 1 kilogram of air, wouldn't it? How many of those straws would fit on a 1 meter by 1 meter place? Let's think about that. 1 meter is 100 centimeters, isn't it? What's 100 centimeters times 100 centimeters? So what's 100 centimeters times 100 centimeters? 10 to the second times 10 to the second is what? 10 to the fourth, which is 10,000. So how many straws could I put on this table all the way to the top of the sky? 10,000. 10,000 straws, couldn't I? Each straw would have how much air in it? 10,000 kilograms. Each straw would have a kilogram of air. One more time. Each straw would have a kilogram of air. How many straws could I put on a square meter? You said 10,000. So then if I had 10,000 straws, that'd be 10,000 kilograms of air sitting on top. You don't believe that? And how many newtons? What's the weight of that air? All right, I'm going to do a little demonstration here, and I'll try to prove to you that there's a tremendous amount of air sitting on top of this table. I'll even use the table back then, okay? I'll show you that in just a minute. I do want to tell you this, though. This word called a Pascal, you read about it last chapter, right? They defined a Pascal as how much 1 Newton of force per square meter. I have a lot more than that sitting on that top of that table. So what I have 100,000 newtons sitting on a square meter, right? So what is the air pressure on top of that table? Let's see, 1 Newton per square meter is a Pascal. I have 100,000 newtons. It's 100,000 pascals. Now, humans don't like saying the number 100,000, so how many kilopascals are sitting on top of my table? About 100. So one way of saying the pressure, air pressure, is in kilopascals. It's about 100. Okay, now we're going to get into these numbers, and I'll show you more than one day, but that's one of the harder pages to understand. Is that I think I'd like to do a little demonstration showing you that, and try to prove to you that. And by the way, later next week, I will show you about somebody in the 1600s. In the 1600s, he was so impressed with the idea of air pressure and what you could do with it that they started making had vacuum pumps. So they started making a vacuum pump. And this one guy, you'll see him next week. Not really him, he's dead. But you'll see him on the internet. I'll show you a picture of him on the internet. And he had 8 horses, really workhorses. They were this way, 8 more this way. He took a disc, it's about this big, he made out of the metal, and it's a sphere, and these are hemisphere, get it? Now because you put 2 pieces of metal together, you can't always seal them very well, and you guys know about the word gasket, there is a word gasket. To get 2 pieces of metal to seal, you sometimes have to put something in between there that will seal them, you get it? And like my engine has a gasket, gaskets between the head of the engine and the other part of the engine, or anyway. So anyway, what they did, they used oil-soaked leather as a gasket, and he put them together, hooked it up to a vacuum pump. And since he had this thing, he took all the air out of the inside. Okay, that's all he did. No glue. There was no glue. And the 2 hemispheres were being pushed together. Okay, then he had those 8 horses going that way, 8 horses go that way. They could not pull the hemispheres apart. And yet when he told the horses to stop, and he opened up the valve and the air rushed back in, the hemispheres fell apart. In the 1600s, they realized how powerful air pressure could be. So let me see if I can show you this. I don't want anybody to get hurt, so I'm going to let me do this demonstration. Okay, so I have done this demonstration many times, and I will tell you that I cannot tell you it works 100% of the time, and I can tell you that 20 years ago, it would work almost 100% of the time. And then I noticed something that I should have figured out anyway. I used to always use newspaper, and so this would be the first year I won't be using newspaper. I could use a newspaper. I might try it. I might try newspaper.
Let's try it.
They are making newspaper cheaper and cheaper than they ever have. It's thinner and thinner than they've ever made newspaper. They probably figured out they need to save money to stay in business. And they probably figured out a lot of people get rid of them after one day, yes? And I think they figured out they can make it pretty thin and you'll still buy it, some people, right? So I'll try it. I'll try it with a newspaper. And if it doesn't work, I'm going to go with paper that I know is not so thin. So we'll try it. So what you do is you get a table. I have a table here. And what I'm going to do is I'm going to try to tell you that this table has a huge, huge amount of air sitting on top of it. Okay? And so what I'm going to do is I'm going to take one of these paint sticks and lay it right there. I want to prove to you, first of all, I'll take 3 of them. I'll take 3 pieces of paper, and I'm going to prove to you that the weight of that paper is not very much. Watch. Okay, so there's no way that the weight of that paper can hold down that stick. Does that make sense? There's no way that this paper weighs enough to hold the stick down. So I'll take a piece of paper. The same thing. Now, all I'm going to do here is, I'm not gluing it. All I'm doing is, I want to make sure that there's air on top of the paper, but I don't want very much air underneath the table. You get that? Because then it'll equalize the pressure. So, oops.
They'll just fly away.
Okay, so, ready? You ready? Oh, okay, see? Cheap paper. All right, so now, that might be the last time I ever tried a newspaper. So now, here it is, plan 2. Plan 2. By the way, that was my last piece of newspaper. I don't get the newspaper anymore. I don't get the newspaper anymore.
Yeah, it's still making it right.
But they are making it, I'll tell you one thing, they're making that newspaper really cheap. Again, all I'm doing is I'm trying my best to figure out, I'm going to underneath the paper. There you go. All right, try again. Oh, golly.
Double up the.
No, that's strange.
Time to get.
Let me tell you something. That's actually the first time I've never been able to get it with 2 hours. Try it again. Keep paper. All right, give me a break. Come on. Yes. And what I'd like to show you is that the air sitting on top, this much. Yeah, so actually I've never done it before where it failed twice. And there was one time, I remember one time when I first moved into this building, I used to be in a modular unit. And we moved in this building and I said, well, I got some big tables. I think we'll use one of the big tables. And it failed and I thought, what's going on here? And look at the table, you'll see something. What do you see there? I didn't even see it. I covered it up with a newspaper. I didn't even remember. I didn't even think there were holes there. And so what happens is air is able to get underneath the table. It's going to equalize the pressure there. And so I learned my lesson there. Now here, well, if you want to get it away from there, you get away from that hole. Ready? Wow. Okay. I'm going to tell you that I'm going to do this again next week. I have never not done this. I have never not been able to do this thing. I do. I don't know. I thought maybe that paper was good. But I'm out. I had to go out and buy a newspaper. I did this for the elementary kids 2 weeks ago, and I only had this much.
Do they have names?
So I'll try one more. How about that?
I'm about being made, so I have equal,
I am surprised. I'm very surprised.
Is the paper supposed to?
Don't ask the bonus on here or do anything. No? Alright, that is pretty weird. It is. It is. But tell you what, I'm okay with this. I'm okay with it. I'm gonna get another newspaper. We're gonna try it again. Show you, let me show you the demonstration while I'm here. Okay, it's okay. Now, everybody, stay where you're at. Stay where you're at. Here we go. The next one I want to show you is, this is something that you can buy at a hardware store. And this is for people that have, you have a tub, and somehow they either don't have a plug in there, or they don't have one of those automatic, things like that. You can buy one of these and fill the tub up and the water won't go down the drain. And so this is a pretty simple little thing, okay, pretty simple. And I'll just lay it right here. And I'm going to ask you, Parker, do me a favor. You just, there's a little handle right here, just pick it up and hand it to me. Go ahead.
Come on, Parker.
Oh, I did not.
Do it again. Keep your face straight up.
Don't pull it off the desk.
Straight up, Parker, come on. Parker, come on.
So, what's interesting about this is that you never think about that. When I do that, it pushes the air from underneath it out of the way, and there's really a lot of air sitting here. Try it. There's a lot of air sitting right on top of it.
No.
And so the air, now, of course, if you want,
Air
to
says
do it
no.
again, if you want to get it up, all you need to do is let the air underneath it equal, like you like that. Woo! So you start thinking about air pressure a little differently. These right here are for toilets, and so this is from my house. And
Jeffrey's very rare.
no, it's never been used. It's never been used as a toilet. I bought one of these just for physics class, but you've seen these before. They're called plumber's helpers, and so what you do is you say, well, that's a suction cup. Well, I can tell you right now, watch. Nothing is sucking. Is the table sucking? Does the table have the ability to suck? Does this rubber have the ability to suck? I mean, if it did, then go ahead. Go ahead, start.
Suck my face.
So, no, so it doesn't. So anyway, but when I force the air out, when I force a lot of the air out right there, then this air here is going to try to get in and equalize that partial vacuum. And so what happens is,
Pick up Tucker's desk.
and you see that. Now I know what you're thinking. You think, well, it's sucking. It's not sucking anything. And all you need to really do is, all you need to do is Let air underneath it. If I get air underneath it, then it will equalize the pressure like that. Okay, I'll pass this around and just, like I said, just don't bend it or anything like that.
Yeah.
Just see if you can pick it up. And if you want to try that, you can try that one.
Yes.
Just wait.
Alright,
It's like
take
a
my
hockey
stuff out.
puck.
I gotta see, can I lift my desk?
No, Leah, let me do it. Come on, play.
Oh!
There it goes.
Hey, you got it all.
I got it out, guys.
Alright.
You did it.
You got it, dude. Just